Okay, everybody. So we were talking about, in the last clip, we were talking about the nuclear particles and what type of reaction. We talked about our type of nuclear changes. We talked about transmutations. And we talked about the types of particles. We looked at alpha particles, beta particles, gamma rays, and the like. And in this one, I just want to go over and discuss like how we get these particles, why we get these particles. Can we predict what type of particles we're going to get from a certain isotope? So with that, we look at something called the band of stability. And simply, this is a plot, really a plot of all of the stable isotopes. Okay, so according to their numbers of protons and neutrons. So that's what we look at here. So really what we're looking at is protons on the X, okay, and sometimes that's given the symbol Z. Okay, not too much to worry about there. And then the neutron number is N. So you have neutrons plotted here. So we simply take an isotope, we find its protons and neutrons, and we plot its protons and neutrons in here. And these little blue dots are the stable isotopes. That's why we call it the band of stability, is this band, okay, is the stable isotopes that do not emit radiation. So they're not radioactive. Okay, and what we do is we draw a line, and this line signifies where the protons and neutrons are equal. So if you had 10 protons and 10 neutrons, you would be right there on that line. If you had 20 protons and 20 neutrons, you'd be on that line. If you had 40 protons and 40 neutrons, you'd be on that line. So what we find is that as we plot the heavier and heavier elements, again, your atomic number is the type of number. Remember, the proton number is the atomic number. As we start plotting all of the isotopes, we can pretty much be on that line for the lower mass elements. It's only when we get to about atomic number 20, which is calcium, is where this line begins to skew to the left. And we begin to bend this band of stability ever so slightly off that 1-to-1 ratio line. And that simply means that the 1-to-1 ratio of protons to neutrons is no longer stable once you get about right here. Right? You need more and more neutrons as you move up in atomic number and as you get a larger mass elements before you finally exhaust the whole thing around 84. So again, we talked about 84 being where you don't have any more stable isotopes. So the band of stability really ends here. Now, what's so significant about studying the band of stability is that what happens if you are here? What if you have protons and neutrons here? What if you have protons, neutrons here? And what if you have protons and neutrons here? Because you can be off the band of stability. And if you're off that band of stability, you simply will emit radiation to get to the band of stability. So if we are above the band of stability, a nucleus wants to go down towards the band of stability. If you're to the left of the band of stability, you want to go down to the band of stability, to the right. And if you are to the right of the band of stability, you want to get and go to the left. So each element that is off the band of stability wants to get to be stable by finding its spot on the graph. All right. So we want to look at these different scenarios. Where are you on this particular thing? Now, let me start off by saying also that this is not a hard fast rule, which means there are some nuclei that do not follow what we think they follow. And they don't follow a specific rule. They simply do what they want to do. So this is not exactly a rule, but more of a guideline. Okay. So really, just what does this do? Okay, the band of stability is simply. Let me get this pen right here. The band of stability simply represents a plottable number of protons versus neutrons that produces stable nuclei. Okay, remember, these are the stable ones. We're interested in the ones that are off the band of stability. Any nucleus with a neutron to proton ratio outside the band is radioactive and emits radiation. Okay, all of the isotopes of elements greater than 84 are going to be unstable. Okay, so that means that would be this area up above the band of stability. Okay, so just some important parts of neutrons. For lower mass elements, okay, a 1-to-1 ratio of neutrons to protons is very stable. Okay. More neutrons are needed to keep the nucleus stable as atomic number increases. Okay, so that's really, really important as we go forward from this particular thing. So that's what the band of stability will tell us. All right, so a little information about this in general is nuclei, again, can be unstable in these three ways that we talked about. The first way we talked about, we can talk about is really is the number of neutrons. Let's just say you have too many neutrons, which means let's just say you're here at atomic number 20 and you have 30 neutrons. So that would be a lot of neutrons that you're way above the ratio of the 1-to-1 down here. Okay, in that case, you're to the left of the band of stability. Okay, and what happens there is what we find that we normally emit beta decay or beta particles. Emitting beta particles is known as beta decay. Now, a beta particle is your E, is your electron. Now, electrons coming from the nucleus is really strange. Okay, so I want to just take a look at. I'm going to put the next line up only so I can know what to do here. Okay, so let's just say that I have a nucleus, say carbon-14. Okay, and carbon-14 has 8 protons and 8 neutrons and 6 protons. So it's not in a 1-to-1 ratio. It's actually off the band of stability. All right, so what we're going to find is that carbon-14 will actually emit a beta particle, so that would be emitted, okay? And what would be left over would be nitrogen. So 7 minus the 1 would be 6, okay? And nitrogen would actually be what would be formed from them, okay? And you can see that we went from 8 neutrons to 6 protons. Now we have 7 neutrons to 7 protons. So notice that we now have a 1-to-1 ratio when we weren't before. Okay, and that can happen in that case. So really, what's really happening in this? How do you release a beta particle or electron from the nucleus? And that's really a little head scratching, because generally we're not talking about electrons that are in the electron clouds. This is actually coming out of the nucleus. So what scientists have found, and if you want to think about this on your own before you look, we can pause it. Okay, we're back. All right. What scientists have found is that we've taken a neutron is really made of a proton and an electron. So if you think about that, if a neutron breaks down and decays itself into a proton, okay, it would release the negative part of itself, which would be the beta particle. That would be emitted, okay, or shot out of the nucleus, and the proton would remain in the nucleus, okay, because it used to be a neutron. So it turns into a proton, which raises the atomic number by 1, and then you emit this as radiation, and that would come out of the nucleus. Okay, and you can see the numbers make sense. 1 here equals 1 plus the 0, and the 1 and the 0 here is equal to 1 minus the 1 here. So again, you have this conservation of mass here. And you can see it in the equation too. You can see that carbon used to have 6 protons. It has now produced a proton, which raises the atomic number. Okay, and again, that equalizes out. So again, beta decay is usually when a nucleus has too many neutrons. All right, very similar something happens to when you have too many protons. Let's say you're to the right of the band of stability. And if you're to the right of the band of stability, you would be over here in this section. And in that case, you wouldn't have enough neutrons. You would actually have too many protons. You could think of this as two things. You could think of it as either not enough neutrons in the terms of neutrons, or too many protons. Okay, so this is going to result in positron decay, okay, or electron capture. And again, remember, a positron was our E with the 0 and the plus 1. Okay, so that was it was like a positive electron. So I'm going to give you an example here of maybe, let's just look at neon 19. So neon 19 is an isotope that's going to release a beta particle, but a positron. So what happens with beta particle and positrons is you can see neon has 10 protons, but it only has 9 neutrons. So it's got 1 extra proton. So what we're going to then produce is 9 plus the 1 would be fluorine, and fluorine would be 19. So you can see when you write this reaction, 19 would equal 0 plus 19, and 10 would equal 1 plus 9. Okay, so what's happening here is you're taking a proton and you're doing the reverse, right? You're taking protons and breaking them down to neutrons so that we can equalize the number of protons and neutrons. So how do we actually do that? Well, we can take a proton in the nucleus, we can convert it to a neutron, right? And then emit the positive part of the proton. The little piece is the beta particle, or your positron. Then, so again, that would be emitted. And again, you don't necessarily have to be able to write this. You just want to understand where these particles are coming from. Why do we emit these particular particles when we do? It's because we're looking for stability. All right, so notice that a proton is really a neutron is equal to a neutron plus a positron, just as a neutron is equal to a proton plus an electron. So that's where you get, now this can happen in two ways, not only just a positron decay, but you also can have electron capture, and this is a little freaky. All right, so how else can you make a neutron? Well, another way that you can make a neutron, okay, is taking a proton, okay, and reversing the process in number one. So what we can take is we can take a proton and we can add an electron to it, and those numbers should equal a proton, right? So 1 plus 0 would be 1 at the top, 1 minus 1 would be a 0 at bottom, what would result in a neutron. So you can see in both ways, we've produced a neutron by getting rid of a proton, or almost neutralizing a proton. Okay. Now again, my question is, like, where are you getting this from? Like how are you getting this electron? That's going to come from the electron cloud, which is really strange. So actually, the nucleus reaches out and grabs an electron from the electron cloud, typically from the 1s level, because that's closest to the nucleus. All right, so I know this is getting deep. I know there's a lot here, but don't worry about the inner workings of all of this, to memorize it all. It's just you want to understand where this is coming from, okay, and understand it. Okay, so the last step is really, you can just be too darn big. I mean, you can have too many neutrons, too many protons. You can be off in your amounts of these in the ratio, but you can also just be too big, and that's going to result in just losing weight. And the best way to lose weight is your alpha decay. That's the best way to do it. So again, alpha decay is just releasing, 4 particles. You're gonna just release a helium atom, basically, from this, or a helium nucleus, where you're going to just release 2 protons and 2 neutrons. Again, you think of 2 protons and 2 neutrons as this particle. So if you have excessive weight, you have to lose weight, and you're a nucleus, this is the best way to do it. So a good way to do that is to take, so you think of a heavy nucleus like uranium-238, which is element 92. That would be way above the band of stability. You would then lose that alpha particle. So I'm gonna pretend the alpha particle is to the right here. You would lose that alpha particle here, and then what element would be resulting? Well, what's 2? How do you get a 92 from 2? Remember, think of this as equals. You would be an element 90. That would be element TH from the periodic table. Okay, if you have 238, how would you? And if you subtract 4 from it, you would get 234. Okay, and this would be the emitted particle. All right, and notice that you've now gotten lighter along the way. All right, so that's your different ways. That's the way the particles are done. Again, not all elements follow these rules. If you want to think of the band of stability in a different way, here you would have too many neutrons. Here you had too many protons. Okay, and here you would just be too big. And again, you want to get there. You want to get there. You want to get there. Okay, and that's the way you would have to do that. You would have to reduce your neutrons. You'd have to reduce your protons, or increase your neutrons. Okay, and you'd just be too big there. And again, once you get into that band of stability and you're a nucleus, then you no longer will have to do anything with radiation. All right, so there's your theory behind this. Again, we can be used as a good idea for prediction. Yes, I may ask you to predict these, and again, you would have to know your basic regions of the graph. I wouldn't get too crazy, but I would be able to explain the band of stability. Okay, and we'll take it next time I see you. Have a good day.